In this video, I'm going to solve another Archimedes principle buoyancy problem. And this time, the given information that you're going to start with are going to be the substance, which is going to be iron. The volume of the iron is going to be 0.0750 cubic meters. And then the densities from the density table. Density of iron is 7.8 times 10 to the third kilograms per cubic meter. And this time, instead of it being immersed in plain water, it's going to be immersed in seawater. So you're going to need the density of the seawater too. And again, these come from the table in the textbook, and of course you can look it up online too. 1025 kilograms per cubic meter. All right. What we're going to have this time is we're going to have a container filled with seawater, and the iron, the chunk of iron, is going to be resting on the bottom. And we are going to once again find all of the forces that are associated with this. So step one can be drawing a free body diagram. We've got the force of gravity of the iron. We've got the buoyant force, mg of the fluid. And we've also got the normal force of the bottom of this container pushing up on it. And remember, as we go through these different exercises with Archimedes' principle and the buoyant force, the force of gravity of the solid is always going to be this. The buoyant force is going to always be mg of the fluid, or rho vg of the fluid. The force, the other upward force that there's going to be when there is a third upward force, can vary. It could be the force of tension or the normal force or the apparent weight or whatever. Realize that this can be called a variety of different things. All right, this system is in equilibrium. The sum of the forces equals 0. So we can go straight to the equation without a lot of difficulty. We recognize that the force of gravity downward must be balanced by the two forces upward. Okay, we are given the volume. We have the densities of both of these things. So the other key in Archimedes' principle is recognizing that the displaced water is identical in volume to the volume of whatever it is that's doing the displacing. In this case, the iron. Because we have volume and density, rather than needing to use mg to do our calculations for the force of gravity and the buoyant force, we could use this form of the equation, the density times the volume times gravity. So let's do that. Force of gravity equals, so this is going to be the iron. Okay, I put these subscripts in here because many times people will mess up. They will be thinking, oh, I'm going to find the force of gravity of the displaced fluid or the buoyant force, and they'll mix up the densities. Okay, you've got to be sure to keep these straight because this formula works for both the buoyant force and the force of gravity. When you're talking about the buoyant force, the mass, the density had better be that of the fluid. When you're talking about the force of gravity, the mass and the density need to be that of the solid. All right, here we go. 7,800 times our volume of 0.075 cubic meters times gravity of 9.8. And I got 5733 newtons, which we should round. If we look over here, let's make this a 3 sig fig problem. That would round to 5730 newtons for the force of gravity on that chunk of iron. The buoyant force can be calculated the same way, except using the density of the salt water. So the buoyant force this time is going to be 1025, 0.075, 9.8. When I did that, I got 753 newtons. And then for the normal force, for our final step, we'll simply take the difference between those two. 5733 minus 753. Again, hang on to sig figs until you get to the end and then round. And I got 4979.6, which would round to 4980 newtons for 3 sig figs. There you go. When we begin with volume, it is pretty straightforward.